Welcome back, everybody. This week we've talked about logic. We looked at logic gates. We looked at the symbols for those gates. We looked at the truth tables to represent the gates. And we also looked at something called Boolean algebra, which is the algebra of logic. We know that each gate has a symbol, truth table, and the Boolean expression. Now what we want to do is to try to understand how we're going to implement that logic in the PLC, the Programmable Logic Controller. So this PowerPoint is about the fundamentals of logic as applied to the PLC, and we're going to deal with what's called word-level logic instructions. So the form in which instructions are implemented to convey commands to any digital device is called a language. So the PLC being a computer, if you want to program it, you have to use some type of language. Now, many of you have probably taken a programming course before. There are many different languages. You might wonder why there's so many different languages. I know when I was in your place in school, I took a language called Fortran, which was oriented towards science and engineering. I became pretty proficient at C programming. You guys, I know you use some math programs, and maybe you've taken some other programming courses. And so you know, in order to get the device to do what you want it to do, you have to be familiar with the programming language. You have to write the instructions the right way, follow correct syntax, and you can write a program and make things happen. PLC being a computer, it's exactly the same. We have to understand the latter. We have to understand the language, but it's different with PLCs because the language is designed to look like electrical circuits, and that's on purpose. That's so that a plant electrician can almost look at a PLC program and it looks so much like a circuit that they can understand it. So we program any digital device, including the PLC, with the language, and the language most common to PLCs is called ladder logic. And so we'll use ladder logic and ladder logic programs to get the PLC to do what we want it to do. So I want to show you an example of that. And if you notice, this is a rung. This looks like the rung of a ladder. And the way the PLC is programmed is you have these various rungs that go on and on and on. And so after a while, it starts to look like a ladder. And hence the term ladder logic program. Now, how do you read this program? Well, these vertical lines here, the way to think about these two lines, think of those as power sources. And think about power or energy, or if you want to think current, for now, just think about power flowing from the left to the right. And these symbols here, the A and the B, you probably recognize those as normally open contacts. And so they're kind of designed to look like that. But actually, that's a graphical language. It's like a pictorial language used to program the PLC. So this symbol can represent any kind of input. So we have these two inputs labeled A and B. And they look like normally open contacts. And then this output right here, you can think of that as a relay coil, but it can be actually, it can represent any output. The thing to remember though is the way you read a ladder logic diagram, you start on the left for each rung and you go to the right. And what has to happen is there has to be, for now we'll say current flow, but that's really not correct. The correct term is logic flow or logic continuity, but we'll get to that at another time. But you can think about this A and B, these what looks like contacts. They're in series, so that represents AND logic. This is an AND circuit or AND logic. The output over here can only go true or turn on or be activated if this contact is closed and this contact is closed. So as I said before, this represents AND logic, but realize this is not a wired diagram. This is all done, basically it's all virtual. This is a program. And so you'll actually have these instructions available to you. A and B represent inputs and Y represents an output, and you'll be able to to manipulate these and design whatever program you want to design, and then download it to the PLC. So this slide, you probably want to mark this slide. It gives you just basic information about ladder logic in general. Each rung is a combination of input conditions, and as I mentioned before, rungs are read from left to right, and then the symbol at the far right, the last symbol on any rung, is an output. So this is always an output. The last thing is always an output. Input symbols are connected in series, parallel, or some combination to obtain the desired logic function. So you know that if I have symbols in series, represents AND. If I have series in parallel, represents OR. I can have a combination of things in parallel and in series, and I can even add to the mix normally open and normally closed contacts. And so we can represent logic using those symbols. And here it refers to a handout that when I email the PowerPoint out to you, I'll send that. I'll also connect that handout, but I will update the class website, and it will be available on the class website as well. Now, program word level instructions. Remember what a word is. For us, we said a word is 16 bits or 2 bytes. And so we understand that words are really machine dependent. But for the machine or the simulation software we're going to use, they use a 16-bit word. And so for us, when we have the ability to implement this logic, AND logic, OR logic, XOR, NOT, we can actually do that bit by bit, or we can do that, we can operate on a whole word. Now, we mentioned in previous classes this device called a register, and we talked about shift registers, if you remember. Well, registers actually hold bits, and our register and word, at one point we said we're going to assume, even though we know a register is an actual physical thing you can hold in your hand, and the word is really kind of made up. It's virtual. We're going to assume a register and word to be the same thing. A register and word are the same. So what we can do here, we can do ANDing, we can do ORing, we can do XOR, we can NOT on individual bits, but what this PowerPoint shows you is that you can actually do those same operations on whole words or whole registers. So what you see here is an instruction that will exist in your simulation software. And remember what we said, we on the left here we have inputs, and the last thing on every rung is an output. Now this is actually an output. This is a command. This is the bitwise AND. So what that means bitwise is you take a whole register and you take another whole register and you can AND those bits together. And bitwise means the corresponding bits are ANDed, and depending on if you have trues or falses in that third register, you'll store the result of that AND. So notice this source A here. Source A refers to this. These represent registers. So source A represents this register, register A if you want. You can think of this B3:5 as an address. You have to have some way to reference the address register. So source A is a register, source B is a register, and this command, what it tells you to do is to take the bits in register A at this address and the bits in register B in this address, and do a bitwise and store them, the destination, store them at this address. And so if you come down here, remember with an AND, the only way to get a true for an AND is for both bits to be true. So I need 2 ones. So here I got a 0 and a 0. If I AND those together, I get a 0. Here I got a 0 and a 0. AND those together, I get a 0. Here I got a 1 and a 0. If I AND those together, I get a 0. The only time I should get a 1 is when I'm ANDing two ones together. So I got a 1 and a 1 is a 1. So here, what this is going to let me know by doing this process is where my bits are all high. If you need to know that in the register for any reason, you can do a bitwise AND, and wherever you see a 1 here, it's representing bits in both registers that are high. Just as there's a bitwise AND, there's a bitwise OR. Now this is called they have it inclusive OR. That's just a normal OR. They're saying inclusive OR because remember you have the exclusive OR where you exclude the condition where both inputs are the same. So this is an inclusive OR. So for it to be true, the exclusive OR to be true, I either need one bit to be true or the other bit to be true, or both bits to be true, and either of those three conditions give me the output of a 1 or high. Whereas if I had an XOR, exclusive OR, the one condition where both inputs are high will give me a false. But this is the inclusive OR, so basically again, you got shift register A, B, they're loaded up with bits. Anytime I see two zeros, a 0 or a 0 is a 0. But anytime I see just one, just a 1 or with a 0 is a 1. So this will let me know when either of my bits are high or both of my bits are high. If for some reason you need to know that, you can do a bitwise OR. It's an inclusive OR compared to this one, which is the exclusive OR. So it's going to exclude the condition where both inputs are 1. So if I have a 1 and a 1, that's a 0. Of course, a 0 or 0 is a 0. The only time I get a 1 is when one or the other of the bits are a high. So here I have a 0 and a 1. That's a high. If you had the other way, a 1 and a 0, then that would be high also. So you have the XOR example. And then this one is the simplest of all. This one, notice that there's only one register. There's one register, one source register, but there is a destination register. So what you're going to do is take the source and you're going to not or invert each bit. So I can flip these bits. I can take the ones complement of it, and then I can store them in another register. Here we're storing them in this destination register. Now remember, flipping bits, what that is, flipping bits is equivalent to taking the ones complement. So if you have to do that, you can just not the bits, and you've taken the ones complement. So that's pretty much it. This is a short video, but we'll talk more about the actual language that we use to program the PLC. We'll get more into some of the details of that. There is one document that goes along with this, as I mentioned. I'll send the video out to you by email. I'll also eventually update the class website, and I'll post that video on the website as well as the document that goes along with it. Guys, have a great rest of the day. Hopefully this information was pretty simple to understand, but if not, you know how to get a hold of me, and have a great weekend, and I will see you soon.